สวัสดีค่ะ How you guys today? I hope that you have been watching the series of my lectures on circuit analysis 1 up to now, and they have helped you in some ways to understand more on the topics. Okay, this sessions will be the last sessions, the last topic for the series of the online course on circuit analysis 1 at the Faculty of Engineering of Kasetsart University, Bangkok campus or Bang Khen campus, Thailand. Okay. Today it will not be long because I will only do the balanced delta Y connections and delta delta connections. Okay, so let's start with the balanced delta Y connections. Okay, so delta Y connection means that on the supply side, our three phase is connected in delta form, delta configurations. Okay, and on the load side, okay, it will be the Y connections. Okay, so A, B, C here. So this voltage source will be VAB. This is VBC, and this is VCA. Okay. On the load side, right, it's balanced load, so therefore the impedance are the same values. Okay, and this is A, this is for neutral point, and this is B, and this is C, terminal C. Well, the current, let's see what else we have. Of course, the current, okay, this is the line current, IA, okay, IB, okay, and IC right here. Well, IB flows, okay, in the line, come here, right, and it flows down here. So this is sort of like a phase current on this side, okay, IA. Okay, so we have IA flowing in here, okay, and of course IB flows like this, goes up here. So IB and IC goes up like this, IC, which means that we would have the voltage drops according to the current. Okay, so plus minus here, right? The voltage drops here, positive, negative, and positive, negative here. Okay, so we're going to assume that on the supply, okay, on the supply, it's a ABC sequence. So therefore, VAB would be a magnitude V phase and angle 0 degrees volt. Okay, VBC is equal to V phase minus 120 degrees volt, and VCA equal to V phase plus 120 degrees volt. Okay, so this is so-called the voltage source from, on each phase. Okay, then let's see if we're going to say that what about the line voltage. Well, line voltage is the voltage between lines, right? So this line A and line B, right? So this is, let's write it down, right? VAB. And if we look at it, right, you see that this point is the same as this point. This B line here is the same as this point. So therefore, it's also the voltage drop across. It's the same voltage as the phase voltage right here. So therefore, VAB is equal to the phase VAB. Okay, VBC is equal to same thing, and VCA equal to VCA like this. Okay, so this line voltages. So what about the line current, okay, and the phase current, So to find the line current in this case, I'm going to do the KVL of this loop. Okay, so let's see. So we're going to write down KVL for loop A, right? A and the capital A, and then down to the neutral point and down to B and then back to A. So this loop right here. Okay, so write it KVL according to that loop. I will get, right, minus VAB plus the voltage drop across this this one right here, right, AN. So IA would be equal to the voltage drop across this would be IA, right, multiplied by the impedance. So therefore ZY IA minus ZY IB equal to 0, right? So this loop passing through this VA minus VAB and go here, positive, the voltage drop here across this VAN, and then minus the voltage drop across this ZY. Okay, so therefore I will get ZY IA minus IB, right, equal to, change VAB to the other side. Okay, and of course VAB, we know that it's equal to V phase 0 degrees, whatever the problem will give the values to you. Okay, so therefore we will get I line A and minus line IB equal to V phase 0 degrees divided by the impedance ZY. So let's call this equation number 1. Okay, we have the expression for the difference between line current of A and B. Okay, but well, we sort of know that IB would lag behind IA by 120 degrees because we have the positive sequence, right? The next value is minus 120 behind that of the one in front, like VAB. So therefore IB would lag behind IA also by 120 degrees. So in other words, it means that my IB would be equal to IA, right, whatever it is, IA, but the angle would be minus 120 degrees behind. Okay, so therefore IA minus IB equal to IA 1 minus 120 degrees, this. Okay, because IB is this IA. Okay, or if you don't see it, I will say IA minus IA angle minus 120 degrees. Okay, or express this in another term, you have IA 1 plus 1/2 plus J root 3 over 2. Equal to root 3 IA angle 30 degrees M. So that's that, right? So now we have two expressions, right? One with IA minus IB equal to this, and from equation number 1 we also have IA minus IB equal to this, V phase over ZY. So therefore we equate them together. Okay, compare with equation 1. So therefore you will get, right, root 3 IA angle 30 degrees equal to V phase 0 degrees over ZY. So therefore you get line IA equal to, right, V face, right, over root 3, right, root 3, and angle 30 degrees and ZY, or in another word it's equal to V face, okay, over root 3 angle minus 30 degrees and also ZY. So you get your I line for IA, okay, whatever you get. Then of course IB would then be minus and 20 degrees, behind IA. So it will be IA minus 120 degrees, and IC is of course, ahead of IA by 120 degrees amps. So therefore this is your line currents, okay. Now, so these are the line currents, okay. What about phase currents? In this case, when we talk about phase current, right, we mean that this is the phase current on the load side. So therefore this one right here, right? But then you see that for the phase AN, right, it's IA, right? So this is IA. For phase IB, for phase BN, it's IB. For phase CN, it's IC. So therefore we can conclude that your phase current is equal to line current. So this is the conclusions, okay, for the delta Y connections, okay. Next one is delta balance, delta connection. So delta connection is not difficult to understand. So we have delta source and delta load. VAB, VB, this is B, this is A, this is C, so VBC, and this between VCA. Okay. Please try to remember it's like A to B, A, B, B to C, look and back, C to A. Okay. And this also have delta load right here, so balance, so the value of the impedance at the load is the same. Okay. And of course this is the line IA, IB, and IC. Okay, so A, B, C. Okay, so of course we have a current. Okay, so if you look first, okay, again assume positive sequence. So therefore VAB, right, is equal to V phase 0 degrees volt, VBC equal to V phase lags behind the VAB by 120 degrees, and VCA is ahead by 120 degrees. Okay. So if we ask you what is a line voltage, again, if you look at this is between the line, right? VAB, let's say, let's go like this, VAB, the line, and if you look here, it would be, right? It's the same. It's the phase voltage also. Okay, it's the same phase voltage. So therefore, the line voltage, actually I should still write VAB small one. VAB, right? Is the same thing as the phase voltage. Okay, same thing. So okay, next the currents. Okay, well, if you look again here, right, the line voltage, if you goes on this side toward the road side, you found out also that the line voltage is the same thing as the phase voltage on the load side. So this is VAB, right? And of course, this is VAB. This is VBC, and VCA, the voltage drop. So the current on the load side on each phase would be in this direction. So this is IAB, right? This is IBC, and this is ICA. So therefore, if you look at the phase current, okay, you see that the phase current IAB is the voltage drop across VAB divided by the impedance of that phase. But realizing that the voltage drop across the phase, the load, is the same as the line and the same as the phase voltage on the supply side. So therefore, this is nothing but VAB over Z delta equal to phase 0 degrees over Z delta amps. Okay, so next one, IBC, right, would be, of course, VBC over Z delta, so equal to VBC over Z delta, right? So it would be V phase minus 120 degrees over Z delta, okay, amps, and so on. And ICA is VCA over Z delta equal to VCA over Z delta equal to V phase plus 120 over Z delta amps. So that's for the phase current. Then what about the line currents? The line currents right here, right? So here, come to this point, and it consists of the two phase currents, so IAB and ICA. So if write the KCL, right, at A, okay, right? So we're going to write KCL at A. So we're going to find the line current. So KCL at A, you would have, right, IA going into the node A, so positive, right? ICA go into the node also, so positive, and IAB is leaving the node A, so IAB equal to 0. So therefore, IA, the line current A, would be equal to IAB minus ICA. So IAB is equal to, right? So it will be, you take the phase voltage over Z delta minus ICA would be VCA over Z delta, and you get the answer, right, for the line current IA, right? Same thing. So therefore, your line current IB would be IBC minus IAB, and IC equal to ICA minus IBC, and you get all the answers. So you can see that the four connections, so this is it for all the four connections that we are going to do. And if you don't want to remember, for example, you don't want to remember, each case, line current, is it line current equal to I phase or phase current or not, okay? You simply have to look at the configurations of your connections and then, trace down, what are relationships. So for example, the easiest one in this case, right, delta, right? We always know the beginning, so-called pretty much the starting point is your phase voltage on the supply side, right? From then on, you continue. For example, right, in this case, you want to find the line current, the line voltage, right? You trace back, look at the picture. Oh, the line voltage is simply the phase voltage, and it's also the phase voltage on the load side. And you continue, reasoning it out from the configurations. Okay. So one example I'm going to do, okay, before we sign off and finish the course, close this course, okay, a balanced delta connected load having an impedance 20 minus j 15 ohms calculate the phase current of the load and line current. So this is a delta, okay? So delta load and delta positive generator, okay? So therefore, okay, if I draw the picture, oops, A, B, C, A, B, C. So VAB, VBC, VCA. Okay, so this positive is positive. So this is VAB 330, 0 degrees volt. So VBC would be 330 minus 120 degrees volt. And VCA is 330 positive 120 degrees volt. And this is 20 minus J 15 ohms, 20 minus J 15 ohms, and 20 minus J 15 ohms. So, well, let's see. So the impedance Z equal to 20 minus J 15 ohms. I'm going to change to polar in case I'm using it later. minus 36.87 ohms, okay, from your calculator. Okay. And the question said find the phase current of the load and line current. So therefore, the phase current R, right? So the phase current is IAB on the load side. Okay, so IAB, okay, IAB would be equal to then, right, VAB over the impedance. So VAB is nothing but 330, 0 degrees, right? Because right here, it's right here, plus minus. And if you use your finger to link this point and this point, you see that it's the same thing as this point and this point, same thing, as if they're parallel to each other. Okay, so therefore this would be, well, since I'm doing the division, I'm using the polar form, minus 36.87. So therefore this is equal to 13.2, 36.87 amps. Okay, well, since it's a balanced system, so your life becomes much easier now, right? Because everything, the magnitude will be the same, but the only difference is that the phase angle is 120 degrees out of phase of each other. And how they are out of phase, that depends on whether it's a positive sequence or the negative sequence. Since this is a positive sequence, so you know right away, you should be able to sort of like figure it out, that then your answer would be, the next one would be 13.2, right? Because the same amplitude, and this would be lag behind 120 degrees. So it would be 36.87 minus 120 degrees. So the answer is 13.2 angle 156.87 degrees amps. Okay. For the next one, ICA, right? Then it's same thing, 13.2, and the angle become 36.87, right? Ahead of the first one, IAB, by 120 degrees. So this would be 13.2. Angle is, oh, sorry, I make a mistake. I just make a mistake. Sorry, this is should be it's subtract, right? 36 minus 87 become minus 83.13 degrees amp, and this is 156.87 degrees amp. Too fast. Okay, right. So therefore that's that. Okay, now the line currents. Okay, so line currents that we say it's IA, right, equal to, using KCL, right, IAB minus ICA. So therefore your IAB is 13.2 angle 36.87 degrees minus ICA is 13.2 angle 156.87. Okay. So therefore, using your calculator, your answer would be equal to 22.86 angle 6.87 degrees amps. Okay. So if you know the first one, right, you can find the answer for the rest of the currents, IB and IC, because the amplitude is the same thing. Okay, and well, IB would lag behind IA by 120 degrees, so 6.87 minus 120 degrees, so equal to 22.86 angle minus 113.13 amps. And IC equal to then 22.86, and it's ahead of IA by 120 degrees, so therefore equal to 22.86 angle 126.87 degrees amps. So these are the line currents. Okay, so pretty much that's what I'm going to teach, okay, for the online, not online, well, online method. okay. So you can watch this, okay. And of course, I will always recommend that you have a textbook, okay. Read a textbook. They explain more details. There are more problems to do, more exercise for you to see, okay. And so this is just for you to get a really some grasp of the circuit analysis one. Thank you very much. Bye.